I'm an engineer, and one of the first examples of engineering I can think of was something that happened in high school. A group of students, including me, were asked to build a bridge between two tables using some saran wrap, some newspaper, and some tape, and not a lot else. We thought about it for like 5 seconds, and we decided we were going to build a bridge based on newspaper triangles because we thought those were very strong. And what we ended up making looked like this. As I think you can imagine, this paper bridge was not very good. It didn't work at all. What I learned from this experience was two things. First off, making something that's a good idea, making it robust, requires some thought. Secondly, don't build bridges out of paper. It's not the right choice and won't work well. Fast forward to the present day, I just finished my PhD at MIT in biological engineering. So I don't build bridges, I build bacteria that work differently and have new functions. Often when I tell people this, like my Uber driver or my dentist, I get the response, "Aren't you playing God?" This is a really good question, and I often brush it off. So today I want to set the record straight, and I want to actually give an answer to this question. Biology is really beautiful and wonderful, and it's inspirational, and it's also imperfect. Like the paper bridge that I built badly in high school, biology isn't robust, and it could be composed of better materials. We can and we should make biology better. The first thing to know about engineering living systems is that it feels super different than engineering anything else. Biological engineering is like discovering that a super messy alien spaceship has like crash landed on Earth, and we need to go through every component and backwards engineer it so that we can understand like the tiniest bit about how it works and have some chance at managing to change what it does. Biological systems are so foreign, so alien. They work and are structured in ways that are so completely different than the way human-engineered systems are built, that it feels a lot like an alien spaceship. And in fact, that's because biological systems weren't made by humans. Organisms are absolutely the most sophisticated machines we know of, and they came about after 4 billion years of random chance. No humans. And it shows, right? In addition to the beauty and wonder of biology, it's also unfinished and imperfect. And today I want to talk about two types of imperfection in biological systems that are the same as the problems with that bridge I made in high school. First, biological systems are not always very robust. And second, they could be composed of much more suitable materials. So first I want to give you an example of a really, really dumb mistake in the human genome that gives people cancer. Normal, healthy cells have lots of little molecular machines called proteins that they use to do all the normal things that cells need to do to be alive. There are proteins that replicate your DNA. There's proteins in your eyes that sense light. Proteins in plants that help them absorb sunlight. Proteins, they basically do all the chemical heavy lifting in living systems. Proteins are physically composed of a bunch of building blocks, which are called amino acids. So to make a protein, you string the building blocks together, and that string will fold up into like the functional version of the protein that performs some sort of function. These molecular machines are so central to having a happy, healthy cell that it's super important that your body is able to manufacture them correctly and also pass on instructions for how to do that to your descendants. And in fact, your genome is composed of those instructions. Each gene in your genome encodes instructions for how to make a protein. When you go out in the sun, you get a sunburn, it will physically damage your DNA, which sometimes will mess up the instructions for how to make one of these proteins. And here's where the problem comes in. One of the most important types of proteins that protects you from cancer are proteins that basically do quality control. They double check to make sure the cell is operating right and protect you from cancer. So mistakes in the DNA for how to make those proteins, those mistakes are especially bad and especially likely to cause you cancer. So over here on chromosome 9 of the human genome, there's two proteins. Both of them are essential quality control proteins. Both of them protect you from cancer. And there's something like fishy about how the instructions are written down, which is that the instructions are written down like on top of each other, but offset by just a little bit using like physically the same piece of DNA. And that means that any mutation in that part of chromosome 9 is super likely to mess up either one or both of these super essential quality control proteins. In fact, mutations in this area of chromosome 9 cause lymphoma and carcinoma, which are both types of cancer. From an engineering perspective, this is just an infuriatingly bad mistake. Just scooch one of the proteins over. Like, they don't have to be encoded on top of each other. In a genome that's 3 billion bases of DNA long, how can you possibly not have space to encode these two essential QC proteins separately? To me, this area of the human genome is like painfully embarrassing. Over billions of years of evolution, genomes will accumulate these errors. It's just heartbreaking because any human engineer would catch this. No one would engineer this deliberately. It sucks because this mistake has caused there to be a ticking bomb in the genome of everyone watching this. A ticking bomb that nature left us as a present to discover. And I think this would be a note I would thus put on the Human Genome Report card. Mostly good, but also gigantic mistakes. It's quite a paradox. There's so much beauty and so many fantastically elegant solutions that nature has presented us, but they come alongside huge mistakes, things nature didn't get around to fixing. And I think we tend to hesitate to criticize biology because of its beauty on the whole. That does us all a disservice because we let our awe of living systems prevent us from recognizing that there are fixable problems that we could improve upon. And I think when people think about human genome editing, they get really carried away in contemplating the morality of like parents editing their children to be tall and blonde and good at basketball. And that's not what's going to happen. Human genome editing is going to be used to correct egregious issues with the human genome that arose because our genome is the result of 4 billion years of random chance. In the history of the universe, no one has ever sat down and been like, how should this work? What would work well? Let's engineer this in a way that makes sense and is a good idea. No one has ever done that. And that's the person I want to be. I want to be the person who engineers nice, clean, robust genomes, and I want to do it with some rigor and really careful thought. I want to add some intelligent design, if you will, into how living organisms are built. So in fact, during my PhD, I worked on making biological systems better. I wanted to make a systematic change that would allow biology to be more extensible. One of the big limitations of biology are the basic building blocks themselves. So there are only 20 different types of amino acids. And when you look at the amino acids, chemically speaking, they're actually kind of boring. Like one very easy way to see this is to look at them on a periodic table. Out of all this good stuff, only 5 chemical elements appear in proteins. This would be like if the alien biology spaceship landed on Earth and we find that it's entirely made out of paper. It's perhaps amazing and inspirational that they managed to get so far, light years, with so little, but at the same time, like, maybe we could get some heavy metals up here, because they're, like, good for things. So in grad school, I worked on genetic code expansion, which is where we're trying to expand biology to include more interesting building blocks that have new properties. I told you before that genes write down instructions for how to create proteins. And the way these instructions are written is actually very simple. The gene is just composed of a list of 3-letter names or codons for each amino acid in the order that they should be added to the string, which will fold up into your protein. What I worked on during my PhD is creating bacteria that have both a very simple and also like very fundamental change. They use longer names to refer to building blocks. So they use 4 base codons rather than 3 base codons. Longer names means more possible names, and thus more possible amino acids. And that would be amazing. Do you want to make proteins that break down plastic bottles? Use new amino acids. proteins that are next generation versions of therapeutics like insulin or interferon. Those can be improved, again, with new amino acids. If you want to make new types of cancer therapeutics that aren't possible today, you have to use new amino acids. Expanding biology to be more chemically sophisticated, this is the future. And so to answer the question I posed at the beginning, aren't you playing God? The answer is yes. We've been gifted with an amazing starting point, a natural world that's full of plants and animals and people, and now we can take it from here. We can take these systems and smooth out the sharp edges that nature didn't get around to fixing, and we can make our own genome more robust in order to prevent cancer. We can expand the fundamental chemical basis of life so that we can use biology to build better stuff. We can, and we should, finally, intelligently design life.